All right, welcome to this episode of Mr. Schilling Does Your Homework for You. Really quickly, we're just going to go through, think about how to think about these different problems. All right, A and B, gravitationally attracted. Don't forget, third law still is in effect. That means that no matter what the masses of these two objects are, there will be the same force of gravity between them, right? And it is an attractive force. So it doesn't really matter what they are. What I'm really comparing is what happens when I change those. So we're looking at Fg is equal to G m over R squared. I kind of spaced that out because I can just look at this and say, now what do? We are going to double both masses. So I got 2m, 2m, and then I am going to also double my separation. So normally I would do two separate instances, but I knew that this was going to happen. 2 squared is 4, 2 times 2 is 4. So I'm actually going to be at the same force of gravity between those. One thing to keep in mind, when we are dealing with the force of gravity, if this is the center of the masses of the objects, this is how we are going to measure our R. The force of gravity between two objects does not depend on the radius of those objects. The only time that's going to come into play is when we are dealing with forces of gravity of objects at the surface of those, planets. Okay. M and M are apart, and the gravitational force on each one is F. The masses are changed to 2m and 2m, and the distance is changed to 4r. What is the magnitude of the gravitational force? So I'm going to show this example, a different way to approach this. I'm just going to say, hey, first situation is the standard situation, G m over R squared, right? That's the first situation, and I want to compare it to a second situation. The second situation is going to be G times 2m times 2m over 4r, and then that 4r is going to be squared, parentheses, particularly helpful here. All right, well, I'm going to go ahead and simplify this down just a little bit so I can see the differences. That's going to be 4m over 16r squared. I can reduce that down even further, and I can see m over 4r squared. And so kind of the point is that since I'm really just, and don't forget the g, I guess. I left it out somewhere. The point here, though, is that I recognize that the g's and the m's, of course, are going to be the same for both. The only difference is what we're going to have with these different numbers. So essentially I can say, oh, F2 is equal to, and it's the same thing as F1, but I can see that it's going to be 1/4 F1, or F1 divided by 4. All right, here we're looking at more comparisons of the force of gravity. In this case, the distance is reduced to a factor of 1/4. So we got to bust out our, complex fraction skills. Again, I'm just going to use this as a reference, but, in this second situation, I'm going to have, looks like I only changed the mass of one object. So that's going to be m times 2m over, I've left the g off. We know the g doesn't matter. And that's going to be 1/4 r squared. All right, so then this fraction is going to be 2 over 1/16. So then that's actually going to multiply up that's going to be equal to, dividing by a fraction is the same thing as multiplying by an inverse. And I'm going to get 32 times, that original force. And if I think about it, the other thing that I can say is, just to see that this makes sense, okay, doubling the mass, that should increase the force. Also, getting closer together, that should also increase the force. And so those factors should multiply, giving me 32. If you're looking at the equation, there is no r for which the force will be 0. It just decreases exponentially. One thing that we can just kind of generally understand here for our inverse square rules, if I have force of gravity between some object and some planet, and r as the distance between the object and the planet, you're probably going to be looking at something that very rapidly decreases, but it's going to just, have an asymptote there at 0. It is never beyond the pull of gravity. All right, so one thing to keep in mind, depending on if we are talking about distance from the center of mass or distance from the surface, whenever we're talking about distance from the surface, remember, I'd say for some object, remember that we're always going to measure that from the center of mass. So if this is r and this is 3r, the total distance is going to be 4r. And so again, we can do that same comparison, but basically since it's over, right, yada, 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 blah, 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 over 4r squared, okay, the difference is going to be, it's going to be 1/16 the amount. Okay. When you're talking about acceleration due to gravity on a planet, you're really just taking the mass of whatever object out. Just like the acceleration due to gravity doesn't depend on the mass of an object when we're doing projectile motion, it's the same idea, except here we're talking about g, and then it's just big M over r squared. And in this case, our distance from the center of the mass, we're really talking about on the surface. So on the surface, you are one planet radius away from the center. So the radius of a planet does have some impact on the acceleration due to gravity. When things get more dense, then that is where you're going to have stronger gravity. Okay? And it says that the mass is 1/2 and the radius is twice, and then what's the acceleration due to gravity? So let's just call this g1, okay? And now I'm going to compare for the second force of gravity. I got g, we know that's not going to matter. I'm going to have 1/2 m over 2r, and don't forget that you're always going to square it right outside. So I'm going to square both of those. That's going to give me 1/2 over 4. And kind of like we said before, well, decreasing the mass should decrease the acceleration due to gravity. Increasing the radius should decrease the force of gravity. And I can see that 1/2 divided by 4 is equal to 1/8. So we've got D. The other way that you can do these things is to take it one change at a time and then just multiply them, right? I can say, oh, this is going to be 1/2, this will be 1/4, 1/2 times 1/4 is 1/8. That's another way you can go about doing it. I totally confused myself on number 7, so I'm taking another stab at it. Planet A is 1/6 the acceleration as it is on planet B, so I can say that the acceleration that is on planet A is equal to the acceleration that is on planet B divided by 6. Okay? And so that's like the ratio that we are getting to. And we're comparing those different masses. So if I substitute our other stuff in there, I'm just going to leave the g's off because I know the g's aren't going to matter. I'm going to say mass of A divided by, and again, remember this is 1/4 the radius of B, is equal to the mass of B over the radius of B squared. But it is divided by 6, so I'm just going to leave that 6 over here, right? And it is the same radius. Now, since I am squaring this 4th and dividing by it, right? A 4th times a 4th is a 16th. And then anything divided by a 16th will be 16. I can rewrite this to say 16 A divided by whatever the radius of B squared is equal to mass of B divided by 6, radius of B squared. And so then I'm going to divide by 16 to do A in terms of B. So 6 times 16 is going to give me 96 D. In this case, we have the same surface gravity, so we want to get the same result. So I've got mass of B over, I don't know why I did this, has twice the radius. All right, so I got mass of B over 2R squared is equal to mass of A over R squared. And it says mass A is like our standard mass. So we want to express mass of B in terms of mass of A. I can see, oh, this is going to be 4. I'm going to multiply that 4 over. So it's going to need to be 4 times the mass, right? Because the force of gravity decreases exponentially with radius, but directly with our mass. So the mass is going to have to change by the factor of r squared. Now we can say one has twice the mass. The planet A has radius r. What is the radius of planet B? It's the same situation, but you see the 2 is in a different spot. So now I have, 2m over r squared, we could call it r1 squared, whatever we want, is equal to m over r2 squared. We'll make this b, oh wait, no. B is twice the mass of A. Here's the mass of A. So how do I get this to be 2 over 2, right? In comparison of these two things, well, this one has to be square root of 2, so that when I square it, it's going to cancel out. So then that should be c square root. Sorry about that. Now we're getting into a satellite. We're dealing with orbital distance. So now we're going to be using the expression, right? G m over r squared is equal to v squared over r. Basically, the mass terms are going to cancel out. At this point, we're comparing the speeds, so I think it's useful to just solve it out. V is equal to the square root of G M over R, right? One of those R's is going to cancel out. And then we are going to assume if there's satellites around the same planet, the mass is unchanging. So we're really looking at the relationship between V and R. And in this case, V is inversely proportional to the square root of R. So if I'm going to compare the two speeds, but one has, I went way too far out because basically the masses are going to cancel. And so if they're at the same orbital distance and they are orbiting around the same planet, then I'm just going to say, well, they're going to have the same orbital speed. The orbital speed is independent of our mass, just like our acceleration due to gravity is independent of our mass. Don't forget, this term right here is really an acceleration. And it's the same type of logic there. Okay. So, in the end, we're talking about the same distance, so we don't really have to use this, but one thing to keep in mind is that T is equal to 2 pi R over V. And so the important thing is for the same orbital distance, the length of the year is going to be inversely proportional to the speed, right? It's going to have the same path, but it's just going to be related. So for example, if it's half the speed, it'll take me twice as long. So I can do this as a twofold thing, or I can just make this comparison for V, but we're still looking at V is equal to the square root of Gm over R. And so again, R is constant, and what have I done? 4 times the mass. Well, I take the square root, and that'll be 2V, right? I'm going to have twice the speed, which makes sense. And, more gravity. I'm going to have to go faster to keep my same orbit. And so with twice the speed, I'm going to end up with half as long for the period of my orbit. Okay, it's kind of a twofold thing. So our orbital period, we have the equations kind of set up already. What is constant for all planets orbiting the sun? So if I'm looking over here and I'm kind of combining these two, right, where I've got T is equal to 2 pi R over V, and V is equal to Gm over R, take a square root of that. Essentially what that's going to end up being is if I substitute this expression into my period, I'm going to have 2 pi R divided by the square root of Gm over R. That is pretty ugly, so just keep in mind we can still do all of our same fraction things, multiplying by the inverse and whatnot. So that is going to end up being 2 pi R times the square root of R divided by the square root of Gm. We're going to say the mass is constant. Remember, R is R to the 1/2. I don't know. As I was saying, R, to the 1 times R to the 1/2 is going to be R to the 3/2. So my period is proportional to R to the 3/2. This one is a little bit different just because of the notation. These really should be exponents. That might make a little bit more sense. I don't have an option for t and r to the 3 halves, but I can square both sides, right? If I square both sides, I'm going to multiply the exponents, so I'm going to have t squared is going to be proportional to r cubed. So t squared over r cubed would give me a constant relationship. So that's going to be C. That one is, I would probably say exceptional in its difficulty level. All right. Now, for these, I don't think you have to do too much. We're just looking at the orbit. We know that we're going to say V is equal to the square root of GM over R. And you would have to use your reference sheet. I don't think I have the. You'd be using the mass, of course, of the sun. And once we solve that, again, we can just say T is equal to 2 pi r over V, right? And that's how I would make that calculation. Or if I wanted to use this ugly thing, I can also say T is equal to 2 pi r to the 3 halves over square root of GM. You can test that yourself and see how that goes. So in this case, you're really making a comparison. Again, you're talking about the sun, and it's Jupiter's orbit around the sun, and then the Earth's orbit around the sun, and then you're comparing the orbital radii that you're going to have. So if you take that equation that we looked at rearranged, let's just start it over again. M over r squared is equal to m v squared over r. Cancel that out. Cancel this out. In terms of r is going to be proportional. I'm just going to say r is proportional to m over v squared. But to use this expression, since we know that the time is proportional to the radius as well, we can make that comparison. I don't have my calculator. I'm not doing those calculations. All right, this is another good example where I can just solve for the mass, right? The mass of the planet in terms, I can actually just pick up where I left off, is going to be v squared times r over our universal gravitational constant. And that's all I got for you guys today.